Hi, this is Professor Fernandez. In this video, we're going to work through example 419 from Calculus 2 Simplified. This is a ratio test example. So we have three series here. We're going to determine convergence or divergence using the ratio test. First thing I want to do is review the ratio test real quick. So I'm going to zoom in down here. I've pasted in the ratio test. This is theorem 415 in the book. It says, let AN be a series with non-zero terms. So that's a stipulation we'll have to check later. Then, so that's the only requirement. There's some conditions here. The series converges absolutely when this limit of the ratio of successive terms in absolute value is less than 1. It diverges when that same limit is either bigger than 1 or infinite. Okay, so you can see that two quick takeaways. First of all, applying the ratio test, right? We want to be looking at a series with non-zero terms. If it has 0 terms, that's going to be an issue, right? Because we're dividing by a sub n. So this is not totally a red flag, if you will. If the series has a finite number of 0 terms, well, then at least you can look at the tail end of the series. And then you can say that the ratio test applies for that portion of the series, which is all we really care about with convergence, right? Eventually, does the series tend to a number, or does it go off to infinity, or just oscillate or something? Second takeaway here is that this limit is really what matters, right? If this limit is less than 1, bigger than 1, or infinite, we get a conclusion, right? So let's go off then and use the ratio test in the context of these examples. Okay, for the purposes of the ratio test, the entire thing after the summation symbol is your a sub n. Okay, so now we're going to go off and verify the two requirements of the ratio test. First of all, is this a series of non-zero terms? The answer is yes, right? N could be 0, but because we're starting with 1 and going off to infinity, it's not in this series. And then 2 to the n exponential function never equal to 0. So indeed, a sub n's are never 0. Number 2, now we're going to find the limit of the ratio of successive terms in absolute values. Sometimes you don't need the absolute values, right? Here, n is positive for all the terms in the series. So is 2 to the n. It's always positive exponential. So actually, we don't need the absolute values here. Make our lives just a little easier. We can drop those. And then now we're looking at the limit of the ratio of terms. So I'm going to start with noting that this is a sub n plus 1 divided by a sub n. So over here, I'm going to write out a sub n plus 1 in a minute, but I'm just going to divide it by a sub n, which I know, right? So I can just plop this in here. Great. To find a sub n plus 1, everywhere I see an n, I put in n plus 1. There's an n right there. There we go. And then there's an n right there, so n plus 1. So now I've created my ratio, a sub n divided by a sub n plus, a sub n plus 1 divided by a sub n. Great. Now I want to do a lot of algebra, right, before we take this limit. So what's the algebra to be done? Well, division is multiplication by the reciprocal. So I just swap where those are in the fraction. And then now I'm going to work on this part. I noticed that n plus 1 over n, I can put that together. And then I'm going to put these together. This is 2 to the n over 2 to the n plus 1. And notice that I have powers of 2 in the numerator denominator. 2 to the n plus 1, rules of exponents, is 2 to the n times 2 to the first. And I have a 2 to the n in the numerator, so that's also in the numerator over here. And from here we see that these two cancel. And I'm left with 1/2. So I can replace this term here with 1/2. So I have limit as n goes to infinity, n plus 1 over n times 1/2. And I can pull the 1/2 in the denominator here to n. And now I'm taking n going to infinity for this rational function. Variety of ways you could do this. You could try L'Hopital's rule. You could use that factoid about limit of rational functions as n goes to infinity, or my favorite, the growth argument, right? So as n goes to infinity, the 1 is like inconsequential, right? This is like a trillion plus 1 is basically a trillion. So down here, I'm left with basically n over 2n, which is 1/2. So actually, this limit is 1/2. And now that I've found the limit, right, back to the ratio test, I need to compare it. This limit happens to be, I need to compare it to 1, right? This limit happens to be less than 1. So the ratio test tells me, hey, this series converges absolutely. right? So that's my conclusion here. So converges absolutely. Great. So now on to the second example, where we'll learn something different from what we just learned, because this one does involve a series that has negative terms in it. So this is in fact an alternating series. So we see here that the ratio test also works for alternating series. Okay, so let's do our basic check again. If I look at this, now this entire thing is my a sub n, are any of the terms ever zero? The answer is no. I have exponential growth and I have something squared, so never zero. They alternate, plus minus, stuff like that, but they're not ever zero. So check for this first one. And then here, I do need the absolute values. I'm going to put them in here, but I'm just going to show you. So n plus 1, everywhere I see an n, put a n plus 1 squared, and then divided by an, which is the original terms in the series. I'm going to show you why. Basically, when you have an alternating series, you don't have to keep track of things so much with the negative ones, because here, right, this negative 1 to the n plus 1 is inside the absolute value. So when I take this absolute value, it gives me 1. Oops, I missed a negative 1 to the n here. This negative 1 to the n is also inside the absolute value. So when I take its absolute value, I also get 1. And then everything that's left over, this and this, they're already positive. These things are never negative. So I don't have to worry about those negative 1 to the n plus 1s or that negative 1 to the n. Because of the absolute value, they turn into 1. Okay, so I'm over here. And what's happening is kind of now what happened before, except the algebra looks a little more difficult, but it won't end up being that much more difficult. Division is multiplication by the reciprocal. There we go. And then I'm going to group together everything that is not an exponential function, and then everything that is, so times 3 to the n plus 1 over 3 to the n. For similar reasons, right? Here, this is 3 to the n times 3 to the first. These 3 to the n's are going to go away. I'm going to be left with 3. And then over here, I can put everything into one fraction and then square it. So that's another one of my rules of exponents. And I'm taking the limit as n goes to infinity of this thing. And so now I get to say a few things. First of all, the 3 goes out front, right? So that's one of our limit properties. And then also the limit can go inside. That's another limit property because I'm looking at a continuous function, something squared. So now I'm taking this limit and same deal. L'Hopital's rule, factoid about the rational functions or growth argument. In this case, that last one says, hey, plus 1, I can ignore that because I'm going to infinity. This limit is tending toward 1. So I'm getting 3 times 1 squared. I'm getting 3. Then I go off and say, okay, that is definitely bigger than 1, right? Always comparing to 1 for the ratio test. Bigger than 1, I'm here in this case. So the series diverges, right? So that's our conclusion for part B. Series diverges. Once we're done with all this, this last example, we will go back and I'll tell you, in some sense, how you could have predicted these things just by looking at the series themselves as a quick way to check your work, right? After you've done all this algebra, for example. Okay, over here, let's analyze this. This is our a sub n. Do I know that the terms are non-zero? Yes, right? Something squared is never equal to 0 unless n is 0, but it's not because n starts at 1. Great, so that's done. And then here, again, ratio test. I'm going to drop the absolute values fairly quickly because I don't need them. All the terms are positive. So the n plus 1 term here is replace n here with n plus 1. So that gets squared. And then divided by a sub n, which same deal here is like multiplying by the reciprocal. Great. And then this is basically the limit we just did, right? N squared over n plus 1 squared. And so same thing we did before. We put this limit inside and n plus 1 squared. And we got that this part tends to 1. So this limit equals 1. And then so here's where we get to the part in the ratio test where we're like, wait a minute, I got something equals 1. So what's going on here, right? It's not less than 1. It's not bigger than 1. It's not equals infinity. So I can't conclude that the series converges absolutely or diverges, right? So when you get 1 for the ratio test, this tells you that the ratio test is inconclusive. I literally cannot conclude it converges or diverges, right? I don't know. So this is a indicator that the ratio test is not going to be helpful for determining whether the series converges or diverges. This is one of the reasons why we have so many different tests in Calculus 2, because if you look at this series, there is a much faster, easier way to determine whether the series converges or diverges. In this case, this is a p-series, where p equals 2, and it happens to be, therefore, bigger than 1. And so we know from our p-series theorem that that tells us that the series converges. So this series actually converges by p-series theorem. And all we had to do to use that theorem was identify the p-value and make sure that it's bigger than 1 to trigger convergence. We actually didn't have to do all of this stuff down here, right, with the ratio test and, the algebra and the limits and stuff like that. So that's my first takeaway. You don't necessarily need to use the ratio test, even though it's the most popular test in Calc 2. Sometimes something much easier will be faster, and sometimes you'll have to use something much easier because the ratio test will be inconclusive. That again happens when that limit of the ratio of a sub n plus 1 to an is 1. Last thing I want to mention, right? Similar insights. When the ratio test does work, as it did in these first two examples, it does require a lot of algebra, right? Finding limits. Going into that, you might want to convince yourself that the series converges or diverges first to sort of anticipate the result. Over here, as we've been saying in the course and in these videos, you have a linear function on top, exponential function on the bottom. This thing is going to 0. These terms are going to 0 so fast that you expect that the series is going to converge. Over here, we have the opposite. We have an exponential function on top, quadratic function on the bottom. These terms are actually going to infinity, and they're going to infinity very fast. So you expect that this series is going to diverge, right? And all of that concurs with what we found. Okay, that's all I have for you.